Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover spanning sets today. This is going to be a 3-video progression. We're going to do spanning sets, linear independence, and then finally the basis of a vector space. So I hope you enjoy. Spanning set. So first we have to talk about a linear combination of vectors. So a vector U in vector space V is a linear combination of vectors, say V1, V2, all the way up to Vn that are in vector space V, if U can be written as this form. So U is going to be some C1 V1 plus some C2 V2 plus all the way up to Cn Vn, where these C's, C1, C2, all the way up to Cn, are scalars. So let's create a linear combination of 3 vectors to create a U vector. So I have U, which is going to be the vector 5, negative 1, 4, and I want to write this as a linear combination of these 3 vectors. So these 3 vectors, this one being V1, this one being V2, and this one being equal to V3. And we're going to use matrices to be able to do this, but I want to show you before I just write the matrix how I created it. So what we know is that this vector, that U, this 5, negative 1, 4, can be written as a linear combination of these 3. Well, that's kind of the claim, right? So it's going to be C1, V1. Well, V1 being the very first vector, 1, 2, 3, plus C2 times the next vector, which is 0, 1, 2, plus C3 times finally the last vector, which is negative 2, 0, 1. Now we're going to do some vector arithmetic in here. So first I'm going to multiply everything by the constant, so distribute the constant through. So C1, 2C1, 3C1. And this is 0 C2, C2 plus 2, 2C2. And then minus 2C3, 0 C3, and then C3. Now, I'm going to add these vectors, and the only way you add the vectors is you add their corresponding elements or components. So then the first component's going to be the addition of the first 3. So C1 plus 0 C2 minus 2 C3. The next one's going to be 2 C1 plus C2, say 1 C2, plus 0 C3. And then finally, we're going to have the last, it's going to be 3C1 plus 2C2 plus 1C3. Remember, that's supposed to be equal to this vector. So I'm going to put this on the other side. Let's say this is supposed to be equal to 5, negative 1, 4. You'll see why I want to do this in a minute here. So 2 vectors are equal when their corresponding components are equal. It means this first piece has to be equal to 5. The second has to be equal to negative 1, and the third has to be equal to 4. So we have 1C1 plus 0 C2 plus minus 2 C3 is going to be equal to 5. Next, we're going to have 2C1 plus 1 C2 plus 0 C3 is going to be equal to negative 1. And then finally, we have 3C1 plus 2C2 plus 1 C3 is equal to 4. And this builds us a matrix. I can write this in augmented matrix form. And I'm just going to write this in columns because I want to see that you recognize it. That this first column, matches that first vector, 1, 2, 3. This second column matches the second vector, which is going to be 0, 1, 2. And that third vector matches this, which is minus 2, 0, 1. And then it's finally going to be equal to this vector, which is the U vector I was trying to build. So 5, negative 1, 4. Now let's call this matrix A, and what I can do is I can row reduce echelon form, say that matrix A, and this is going to give me 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the answers that I get back here are going to be your C1, your C2, and finally your C3. So I'm just going to do this on a calculator. So go to math. So second matrix, go to math, row reduce echelon form. That matrix A that I've already put in there. And then this gives us negative 17, 33, and then finally negative 11. So what I can do is I can I can rewrite this vector as, you know, C1, which is going to be negative 17. So what I'm going to do is I'm just going to rewrite this. So that means 5, negative 1, 4 is equal to negative 17 times the first vector, this 1, comma 2, comma 3, plus 33 times the next vector, which is going to be equal to 0, 1, 2, and then minus 17, or plus a negative 17 times the last vector, which is minus 2, 0, 1. Or, you know, like I said, u is equal to C1v1 plus C2v2 plus C3v3. So I can write it as a linear combination of those other vectors. So this is going to get us to the next step. Is really what I want to talk about is what a spanning set is. And I really want to know if these three vectors span all of R3. So I just proved that they can build this vector. My real question is, can they build all vectors? So if I just randomly say, well, what if I say u is equal to 10, 0, 5, or u is equal to negative 1, 7, 18, and I'm just writing numbers in here. I'm not even coming up with it. I'm just spitballing here. So can I write any vector? My real goal is, can I write u as just any u1, u2, u3? That's kind of my goal here. So let me clean this up and define what it means to be a spanning set using that idea. A spanning set of a vector space. Let S be v1, v2, all the way up to vn, be a subset of vectors in vector space V. S is called a spanning set of V when every vector in V can be written as a linear combination of vectors in S. In such cases, we say that S spans V, or I could say V is equal to the span of S. Okay, so what I want to do is I want to show that this set, which we're just working with, actually does span R3. And what we mean by that is we can say that that C1v1 plus C2v2 plus C3v3, because again, this is V1, this is V2, this is V3, is going to be equal to any vector u. So this is where u is any vector in R3. Okay, so let's kind of set this up. What I mean by that is this is going to be C1 times 1, comma 2, comma 3 plus C2 times 0, comma 1, comma 2 plus C3 times negative 2, comma 0, comma 1. And this is going to be equal to any general vector. So what I'm going to do is I'm just going to say u1, u2, u3. Really, where u1, u2, and u3 are real numbers. So, you know, this would be where u1, u2, and u3 are elements of just, you know, real numbers. So I'm just writing it as a general vector. All right. Now, we could go through the same algebra we did before to be able to get this. But remember, I already had my numbers in here, so I know what we're going to get here is we're going to get an augmented matrix where the first column is going to be the first vector, the second column is going to be the second vector, the third column is going to be the third vector, and finally the fourth column is going to be equal to the equals vector. Now, augmented matrix form really helps us for row reduction, but it's not really going to take us far when we're trying to prove that this actually spans this. So what I'm going to do is I'm going to write this in matrix multiplication form. So I'm going to say, or I can say, you know, 1, 2, 3. I'm saying this in columns because it corresponds to the coefficients of each one of these vectors. And this is going to be equal to some, you know, C1, C2, C3 is equal to U1, U2, U3. So, you know, this and this represent the same thing, augmented matrix form, matrix multiplication form. Now, what I want to prove is that you know, this linear combination builds all vectors in R3. So what I have to verify is that this thing indeed has a solution. And really I can prove that it has a unique solution really by going after this, you know, this coefficient matrix A. So this is of the form, you know, A times, we'll say C is equal to B essentially. Now, in the linear algebra we say AX equals B, but in this case, you know, this is your variable, right? Your C's. So when does this have a unique solution? Well, if I wanted to solve this for x, I know that x is going to be equal to, I'd have to multiply both sides by the inverse, so we know that x is going to be equal to A inverse B, so it's going to have a solution if A inverse exists. And when does an inverse exist? Well, it comes down to being able to find the determinant of this matrix, because remember, A inverse is one of the determinant times the, the adjoint of that matrix, and I just have to verify that the determinant of this thing is not equal to 0. So let's check that. Let's figure out the determinant of this matrix. So 1, 2, 3, 0, 1, 2, negative 2, 0, 1. And if I know that that thing is not equal to 0, and it's not, we know this is equal to negative 1. So this implies that A inverse exists. Therefore, I have actually a unique solution. So this vector is built by a unique solution to this. As I proved before, I showed you actually the coefficients for that general vector I did, that the coefficients were specific. So this means it has a solution, has a unique solution. So therefore, these vectors span V. So therefore, S spans, in this case, our V is R3. Now let's do an example to where it doesn't span it. Actually, I want to do 2 examples where it doesn't span it. And the reason why they don't span are 2 different reasons, and I want you to see why. Because there's going to be a couple different exercises they're going to ask you to do, and it'd be nice to know exactly why this is true. All right, so here are 2 examples. This does S span R3. So what we know we're going to have is, we can write this out like we did before, but I know that this is going to be set up as 1, 2, 3, 0, 1, 2, negative 1, 0, 1. And then this is going to be equal to U1, U2, U3, because remember, to determine if something spans it, I have to show that C1, V1 plus C2, V2 plus C3, V3 is going to be equal to any vector U in R3. Now, when I write this in matrix multiplication form, it really just identifies your A matrix, which is your coefficient matrix built by these matrices, by these vectors, times your general C1, C2, C3, and this is going to be equal to U1, U2, U3. So only thing I have to do is I just have to check the determinant of this matrix here. If this determinant is not 0, then we know it spans it. But in this case, when I find its determinant, we know that it's going to be equal to 0. Which means that S does not span V. This shows that it does not have a unique solution because A inverse exists. So what I can't guarantee that there's unique C1, C2s to build every single one of these things. So S does not span V. Another one to show that S might not span V is if we look at something like this, and I'm going to show you kind of the geometry of this using something like an easier vector space than say R3, maybe something that's like one less dimension. So if I want to show that this doesn't span it, remember that I have C1 V1 plus C2 V2 has to be equal to any vector in R3. So let's set this up, and what I'm going to do is, since I know this is already going to fail, I'm just going to pick 3 numbers, and I'm just going to show it doesn't work for that. Because remember, it's supposed to work for every single vector. So C1 times 3 minus 2, 5, plus C2 times 1, 4 minus 3 is going to be equal to, let's U equal, 1, 5 minus 4. So this needs to be equal to 1, 5 minus 4. If it can't build this vector, it can't build all vectors, is kind of the idea. So now when I set this up, we're going to have, I can write this in augmented form. 3 minus 2, 5. This is 1, 4 minus 3. And this is going to be equal to 1, 5 minus 4. So what I'm going to do is I'm going to row reduce echelon form this particular vector, this matrix. And I'm going to show you that I don't have a unique solution for this. So So what we're going to get, let's go math fraction. What we get is 1 minus 3/5. This is minus 4/5. This is 0. This is 1. This is 17/14. So then what I have is I have 0, 0, 0. So what does this actually say? Ooh. Son of a cup, it builds it. That's cool. What about 0? Oh, no, it doesn't. Maybe it does. Yeah, actually, I can build this vector with C values. That's interesting. What about... Second. Let's go 0. There we go. I want to show this. So, what's interesting about this example that I chose, I wasn't really wise in this vector that I chose. I could go after a lot more vectors in this, but what I've actually shown here is actually these two vectors do build that vector, and I was kind of surprised because usually when I pick them, it tends to fail. But it's interesting that I found one that worked. So really what this says is 1C1 minus 3/5 C2 is equal to minus 4/5. And then this says 0C1 plus 1C2 is equal to 17, 14ths. And I know that C2 is equal to this particular number, so I found a C2. And I could plug that back into here and also find the C1 that works. Now, I did basically show that this thing works because I didn't get some kind of problem down here. So what I did do is I just went back and I said, well, this one works, but I know it's not going to work for all of them because I understand the geometry, and I'm going to show you a picture of this. What if I put a 0 here instead? Because remember, it has to build every single vector, and here's just a different vector. So maybe if your first one doesn't work, maybe try the second one. And what we get here is second matrix. Let's just, sorry, I'm trying to simplify this to a fraction. So math fraction. What I get is for this next one, if I put 0 here, it actually gives me the exact same coefficients, except what I do is I get a 1 here. And at the very bottom, what that equation says is that 0 is equal to 1, and we know that that's not true. So what I can show you is actually these two vectors can't build this one. It could build it with a 1 here, but it can't build it with a 0 here. So all I have to show to prove that something doesn't span it is that it doesn't build every single vector in R3, and there's a vector that doesn't work. So let's get to the geometry of why I knew this was going to fail, so then you can actually use your intuition as well. And that'll finish off this video. So what I'm going to talk about, just like say vectors in R2. Let's just look in R2. In R2, what I know is I'm looking at a set that looks like this, and what I want to know is can I build any vector in R2? Maybe this would be a U1 comma U2. Now, if I say S is just equal to the vector, I would say like 2 comma 0, for instance. I know that can't, we'll even just say 2 comma 0, I'm good with that. So 2 comma 0, what if I just want that vector? All I know I'm going to build with this vector here, and any linear combination of that vector, is just going to be this. This is 2, 0. Boom, that's just going to go to 2, right? And any linear combination of this single vector is just going to be, C1, V1s. That's just all linear combinations because I only have one vector to work with. And I know it can't build a vector that looks like this because it's always going to stay on this x-axis here. So all I'm going to build with this vector is just all linear combinations. So, you know, if I double it or triple it or quadruple it, or maybe -1, -2, -3, or -0.5 or 0.25, and so on, all I'm going to do is I'm just going to build this horizontal axis here. I'm never going to be able to get to, you know, this extra dimension. And the reason why is I have a vector space that only has one vector, but I'm trying to build something that actually has 2 dimensions. So in order to do that, we're going to need at least 2 in here, 2 vectors in here to build out this 2-dimensional space. So what I have here is I know that these vectors live in R3. So for me to fill out all 3 dimensions, I know I'm going to need, you know, at least 3 vectors to be able to do that. And right now all I have is 2 vectors. So what's going to happen here is if I'm in R3, I might have one vector looking this way. Let's do this in color. I might have one vector going this way and another vector going this way. In this case, they might not look exactly like that. But what you're actually going to build is you're going to build a plane that runs through 0, 0, so you'll never be able to get below the plane or above that plane. So you won't be able to build every single vector there. You'll only be able to build vectors inside that plane that it defines, which is what I accidentally did the first time, is I built a vector that was inside that plane. So again, if you're trying to build R3, you're going to need at least 3 vectors. If you're trying to build R2, you're going to need at least 2 vectors. So there's some intuition to determine if something is actually going to be a spanning set. So I hope you liked the video. Please subscribe.